Let's talk about last class. We are talking about the evolution of stars and planets, and we're going to keep talking about that. We're talking about the death of stars today, which feeds into the birth of new stars and maybe the birth of planets. Well, certainly the birth of planets in some way or another. I'll just call some random people here and tell me something interesting. Give me a thought that you had. So she mentions that there's a tremendous amount of planets that we see in other solar systems that are of the size and composition that we don't see in our solar system, which is very strange. And those are between the size and composition of Earth and that of Neptune. We call these mini Neptunes or super Earths, and they turn out to be the most common type of planet in the universe, as far as we can tell. But we don't have any, so what happened to ours? And there's a number of really interesting ideas about that. And most of, I would say, the more conservative theories are that we did have super Earths, and they were destroyed as our giant planets were migrating around in the early days of our solar system. A more fringe idea being that perhaps the super Earths and Neptunes actually cooked down into something more approximating a rocky planet like our own, which is an interesting idea. And there's some interesting evidence to support that. It's pretty far out, but it seems possible anyways. All right, very good. What else do we have here? How about, nice, I'm glad you remembered that. Yes, the difference between a sun and a brown dwarf is just one atom. That is in principle true. Now, brown dwarfs, do you remember the real distinguishing feature between a sun and a star and a brown dwarf? So the brown dwarfs don't fuse, right? They're not crushing atoms together to make new atoms. That's the only difference, which means they don't have their own real power source. They can maybe heat by compression, sort of like we keep bringing up this example of the diesel engine that squishes the fuel and compresses it into and heats it up. They could do that a bit, but they don't have enough mass to actually fuse and squish those atoms into new atoms, which releases a bit of heat. So that's the main difference. But at the end of the day, it's a kind of arbitrary threshold. At some point they have enough mass, and at some point they don't. So we'll keep coming back to that idea over and over again, because I think it's gonna pop up as we talk about the various ways that stars can die. Because the more popular stories, the ones that appear in your textbook, the way that stars die are quite extravagant for the most part. They explode or they turn into these white dwarf objects, which we'll play with. But it seems to me that there's a very reasonable possibility that they also just lose an atom and they can't fuse anymore. So they actually turn into something that looks a bit more like a brown dwarf, which of course looks a lot like a Jupiter. Jupiters aren't technically over the brown dwarf threshold. I guess I should clarify this. So brown dwarfs actually can fuse a really heavy version of hydrogen. They can't fuse natural hydrogen. There's a heavier hydrogen that has an extra neutron that brown dwarfs actually can fuse. And that distinguishes them from Jupiters, more or less. But they look the same. Their composition is the same. And of course, the composition of Jupiter is almost identical to the sun. So they're very, very, at least superficially similar looking bodies in terms of their appearance and structure and their layered structure. We'll get into that in a little bit. Cool. So she mentions the thick atmosphere possibility of the past. Yeah, I mean, that's one that a few people have developed, and it plays into this idea of the super Earths evolving into something more like the Earth, or maybe the Neptune-like planets evolving. I don't know why that one's not more popular, to be honest. I've looked at it quite a bit. It's a really interesting idea, and of course, if you guys want to learn more about that, there's an astronaut. His name's Don Petit. We had him on the podcast a long time ago, so I can't vouch for the quality of that one, but it was a very interesting discussion nonetheless. And he wrote a paper with Octavio Levenspiel up at University of Oregon about this idea, and it's very compelling. Of course, they only imagine that the atmosphere is 3 times as thick, which is what you'd need to get those flying dinos to stay in the air. But of course, we know that we firmly believe, most people, I think it's fairly convincing, that the Earth was struck by a pretty serious chunk of rock about 60-ish million years ago down in the Yucatan Peninsula. And that might have been a really good opportunity to lose some atmosphere too. It's not really discussed, but it's hard to imagine getting smacked with something that big without vaporizing a good deal of the air in the process and kicking it off the planet. So there's been ample opportunity over the years. And by the way, that wasn't, we talked about this last semester, but that wasn't a unique event particularly. The Earth is constantly being hit by these nasty asteroids. And it's amazing that any life persists through all of these, but it does somehow. And ones that are even half that size would be almost equally devastating. But it's thought that something that big, I forget, does anybody remember the size of the Chicxulub meteor? I want to say it was on the order of 10 to 20 kilometers across. That essentially vaporized the entire face of the Earth. I don't think that it moltenized the rock all over the Earth, but certainly boiled the oceans and so forth. It was really, really nasty. So, we have ample opportunity for impact events to disturb the atmosphere. It doesn't necessarily have to be a migratory thing where it's standing next to the sun. And actually that idea that the planets could change positions, well, it's important for standard astronomical planetary formation science. It's important in the early days because we have to move Jupiter around, we have to move Neptune and these guys around in order to have them be at the right temperatures to form and so forth. But people don't really consider it in the later years, let's say in the last, the historic years, well, prehistoric, but geologic years for Earth, right? In the Earth's rock record, we don't consider the Earth to have changed orbits. But it's a tantalizing possibility that these things might happen, and they could explain a lot of the strange moments. One of my favorites, I think I mentioned before, is this period called Snowball Earth, which is very, very bizarre. There's never been a period like that where the entire Earth is covered in 5 miles of ice. That only happened once, and nobody really knows why it happened. So something strange happened, something that wasn't part of this periodic natural rhythm of things that we like to lean on as our predictable patterns here on this planet. So could that have been some sort of orbital change? I don't know. I wouldn't rule it out. Okay, cool. Let's do a couple more. I want to get through this list. Well, those layers can start to fuse then too as that heat appears, yeah. Cool. All right, that might be a good place to just keep rocking because we are going to pick up with that story and get into the details of it a little bit. Because so I'm just going to review for people who are like watching this video online, is you kind of reviewed for us this process by which a star, say like our sun, eventually exhausts its hydrogen fuel in the core. And it's all turned into helium for the most part, which is just basically 2 hydrogens smashed together for, let's be overly simplistic about it, the second most simple atom, let's say. But it's not hot enough in the core to fuse those heliums together. The bigger the atoms are that you're trying to squish together, the more energy you need, the more temperature. Remember, temperature is just motion, right? It's just this frenetic, chaotic motion of the atoms with displacement motion, really. They're crashing into each other. You don't have the temperature to do that, but so the star, essentially, its furnace shuts off in its heart and deep in its core, but gravity now takes over because it doesn't have that expansive pressure from the internal fusion reactions. So gravity takes over, it crushes down, we get the car piston situation again, heating begins to take place. Still not hot enough to heat and fuse the helium, but the heat dissipates outward convectively, and it starts to heat that layer of hydrogen outside of the core that wasn't hot enough to fuse before. And that layer takes over, and it begins fusing. And so you get this, and this can happen several times. And this actually, as it sparks, it leads to a flash of heat, which actually expands the star a little bit. And as these things unfold, and I'm going to get into the details of those presently, you actually start losing layers of the star. And this is really interesting. Because we have an example of this happening in our night sky right now, which you can actually go out and see if you want to. It'd be nice to have a telescope, but you can see this with the naked eye. This star up here in the shoulder, the color's not really coming through very well here, but in the upper left-hand shoulder of the Orion constellation, there's this star called Betelgeuse. Now, Betelgeuse is well, it started off as a much more massive star than our own. It's still much more massive. Huge star. But it's essentially going through this same kind of transition, right, where it's swelling periodically. It's casting off layers. Now, Betelgeuse, there was this mystery going on the last 5 or so years where Betelgeuse got so dim it almost was blotted out. And people were trying to figure out what was going on because that didn't quite fit, right? It should be swelling and maybe contracting as these different layers start fusing and stop fusing. But the dimming was not commensurate with that. And what people have essentially reckoned at this point is that it's actually casting off layers of its outer surface as it's going through these different convulsions, essentially. And so, you know, day to day, this thing actually changes in brightness, and something you can actually, if you start paying attention to it, you can notice it. It's very, you have to watch it every day to really get a sense of this, but it is pulsating on a regular basis. And part of when it gets really dim is because there's a big layer of, you know, as that material from the surface comes off, it cools really rapidly, right? And it starts doing all of those things that cold atoms do, right? It's condensing, and you're getting dust, and you're getting material that the light can't shine through, essentially. So this is kind of a cool real-world example of this process happening. Now, Betelgeuse it's funny because, and this will make sense soon, but it's only supposed to be like 10 million years old, this star, which is wild because our stars stop at, you know, even conservative estimates to be billions of years old, right? At least, you know, if our planet is at least 4 billion years old, then the sun must be at least a bit older than that. This thing is only thought to be 10 million years, and why is that? Well, the idea is that when you have a really big star, it goes through this whole life cycle much faster than a really slow star because it doesn't have because it has so much stuff crushing down on it. The fusion reactions are happening much faster, and it's burning through its fuel much quicker as a result of it. So this interplay between how much matter you have in order to, like, the stars that are the most stable and long-lived are the ones that are really have enough. They do have enough matter to actually fuse, so not just brown dwarfs, but they don't have so much matter that they cook it all off really fast. And so this is going to make sense when we talk about the timelines of how we date the ages of these stars. A lot of it comes down to how big are they, and how would that theoretically lead to their dissipation. Now, before we can get into that, let's talk about these groups too, because this is another way that people date these objects. So we have two basic patterns in which these stars appear in their nurseries and age. The two basic groups here are the globular clusters and the open clusters. The globular clusters are really old, and they tend to occur beyond the plane of the Milky Way, right? They've formed potentially at the same time as a lot of the other stars inside the Milky Way, but they've essentially been cast off, and they've stuck together as a group and moved away from the actual plane. Whereas the younger ones, like the open clusters, there's also these just loose associations which fit into this group too. These are on the right-hand side. They still contain a fair amount of young stars, and they are found actually in the plane of the Milky Way. So let's take a closer look at these. So we're looking here at a globular cluster. These are the older ones, right, that have kind of moved off. The biggest one that we have in our own galaxy is called Omega Centauri, which is about 16,000 light years away from us, and contains millions of stars. And you can see some of the brightest ones are red giants. You can see their temperature over here. And that means that they've essentially moved off the main sequence already, right? They've stopped their hydrogen cooking process, and they're going through some of these convulsions already. And it's interesting because this, in some sense, reinforces the idea that of this story that we're telling about how these things move off the main sequence. Because, well, they contain all of these dying stars, essentially. Now, all the globular clusters are really far away from us. Some are as far as 60,000 light years away from us and quite a bit off the main disk of the Milky Way, which is in opposition to something like this, an open cluster. By the way, of which Pleiades is a really good example. Do you guys know Pleiades? Have you guys seen this one? Anybody drive a Subaru? So Subaru is the Japanese word for Pleiades. If you look at the front little label on a Subaru, you got a Subaru? Sorry, I thought I saw someone raise their hand.
I've been looking at one, though.
They're great cars, I hear. I don't know. When I lived in Portland, it was like you couldn't be a Portlandian without a Subaru. They look really cool. They're a little pricey for me. But anyways, the logo on the front of it, you can go and tell your friends, that's actually the Pleiades cluster, which is one of these young open clusters. Now, Pleiades is actually really interesting. There's a story about the Pleiades in almost every cultural tradition. And what's really fascinating about those stories is that they all surround something like 7 sages in India or the 7 sisters in the Greek tradition. But if you look at the Pleiades, you'll only count 6 stars in it, which is really, really interesting. Now, some astronomers have gone back, and what they've deduced is that in the past, there was actually, well, 2 of the stars have actually at this point gone behind one another. So they look like one star that's much brighter. But in the past, when people were telling these stories, they were more separated out. Because of course, everybody's moving around out there and orbiting one another and so forth. So the Pleiades is a really good example. These things are much smaller than the globular clusters we were looking at before. Their diameter is less than 30 light years across. They're usually fairly well separated from one another too, whereas the globulars are kind of more dense. That's why they call these open clusters. Eventually, it looks like the average speed of each one of the stars in this is fairly high click, and so they'll eventually each escape and separate out from one another, which is kind of what we see happening in our own local system, right? The sun seems to be moving rather autonomously with respect to other stars. Like I said, we don't have a partner that we know of for sure anyways. Most people think the sun does not have a binary partner. And so that fits in with the idea that we're inside of something like an open cluster as well. All right. So what happens? As these clusters get older, the HR diagrams begin to change. And like we were talking about before, most of the stars, the massive stars, use up their hydrogen in their cores. They go off the main sequence and become these red giants and supergiants, as is the case of Betelgeuse. The stars of the lower mass begin to leave the main sequence. They make their way to the upper right-hand side of the HR diagram. This one we're looking at here is a cluster that's about 10 million years old, very, very young. You can see the dense gas around the stars themselves has kind of cleared out. So they've accreted all of that. They've made it into stars, essentially, or blown it away with their stellar wind. One of them's turned into a red giant there. You can see it. It's that kind of orange one at the bottom. And so what does this look like on the HR diagram as they peel off? So one thing you notice is that the stars that have a lot of luminosity, they're very hot and bright, they have a very different peel off. You see, they're coming off of this main sequence at a much higher rate than these ones that have been around for a really long time, right? The ones that are smaller, so they're cooler, less luminous, they actually are going to peel off from the main sequence after much more time, is what this comes down to. So these older clusters look quite a bit different. All right. And I guess this just illustrates the point a bit. Everybody's on the main sequence at first. The really young stars that are really hot and bright, they're going to cook through all of their material much earlier, 100 million years, versus something that might take on the order of 10 billion years to cook off that's dimmer and so forth. Just illustrating this principle that I started off with, that the evolution time seems to depend largely on the mass of the stars. All right, so we have this life story that we've related for these stars. They start off as this contracting protostar. They live most of their life stably on the main sequence, and then eventually peel off the main sequence and become these red giants, right? They're sort of cooler, but brighter because they have more surface area, so more light bulb to shine, basically. After this point, the stories of the stars for different masses differs considerably. So according to their masses, compositions, and the presence of nearby stars, which is also going to feed into it. So we're going to see here in a minute that if you have a star nearby you, it can either contribute, right? You can basically, you're the star, you can drink the material off of that nearby star, or it might take the material away from you, conversely. So those things are going to start to play into the story of how these processes unfold. Okay. So let's review this process of what's actually happening inside of the layers of these things. So the red giants start off with this helium core where they don't start off, but after they've used up their initial fuel, this helium core has no power generation really taking place, no fusion. But the shell of hydrogen around them flashes, right? And then that core, of course, is suffering the weight of gravity. It's heating up, shrinking, growing hotter. Once that core is like 100 million Kelvin, which is an almost unimaginable temperature, 3 heliums actually start to fuse and form a carbon nucleus. So this is a new point in the story that we haven't hit yet entirely. Once that core has collapsed sufficiently, you actually can squish the heliums together. And that's where we think all of the carbon in existence comes from, is from this moment. They can also, we'll get to the other elements here in a minute. Now, why 3 and not 2? That's kind of a reasonable question. Why do you need 3 of these heliums to squish together? Turns out if you squish 2 heliums together, you get a beryllium, but it's really, really unstable. So the beryllium essentially just breaks apart as soon as it forms. So they call this process the triple alpha process, which is kind of an interesting term you might remember for the fusion of carbon into carbon. Does anybody have any idea what's called triple alpha? This is kind of a finer detail, but an alpha particle in fundamental physics is essentially a helium nucleus, right? So it's essentially a helium atom ignoring its electron shell. The helium itself is called an alpha particle, more or less, and so triple alpha means 3 heliums being squished together. So that makes sense. So when the triple alpha process begins in these low-mass stars, the entire core is ignited in this quick burst of fusion, which we call a helium flash. And you get this feedback loop that appears. So as soon as the temperature of the star becomes hot enough for the triple alpha process to begin, that extra energy is released throughout the entire core, super rapid heating, the star flash. The heating speeds up other nuclear reactions in the other layers, right, which provides more heating, which then accelerates the nuclear reactions even further, and you get this runaway process, essentially, this feedback loop, which reignites the helium core in another flash and so forth. So you can get this pulsing effect, and this is kind of what we see in these pulsating stars. This makes sense. Do you guys have any experience with feedback in general? This concept makes sense to you with feedback? Like, I think the most obvious example is with somebody's has on a microphone and it starts to scream back at them. And if you think about it, it makes sense. Like, what's happening there? Well, the microphone is picking up the sound from the speaker of the microphone, which is feeding back into the microphone, or feeding back into the speaker, and you get this loop of amplification. And that same process is happening with regard to accelerating the fusion as the heat builds up, and you get more fusion, more heat, and you get this feedback loop that occurs. Say it again? Yes, it's horrible. It's one of the most terrible parts. Yeah, it's absolutely awful. Okay, so after this helium flash, things get a little bit tricky. So we've moved off the main sequence here. We've talked about moving off the main sequence for the most part up to this point, and that's represented in A. At B, we're talking about this core helium flash, where the helium actually can go into this triple alpha process for the first time. Then something kind of interesting happens. So after this brief period of stability, which is at point C, right at, well, hold on, let me start at B. So after this brief period of stability at B, where we have this helium being fused into carbon, the star actually becomes hotter and less luminous than it was as a red giant, right? As it's kind of starting to act like a normal star again. Its core is fusing. It's kind of contracting in this way. But then it turns around at some point, right? After the central helium is completely exhausted, the star starts to become giant again. So it goes back and swells up again. And you can actually go through this loop several times where it's drifting back and forth on the main sequence like this over and over and over again. The problem is that this is thought to happen so very fast, on the order of days. Like I said, the pulsation of Betelgeuse is on the order of days, right? And so in astrophysical terms, a day is like a millisecond in our own lives. So this is happening so quickly that the modeling kind of breaks down at this point, and people aren't sure really how long they spend in this loop. Eventually, though, these substrates are also exhausted, and the core starts to collapse under its own weight. The heat released by the shrinking of the carbon and oxygen core flows into the shell of helium now. That's just above, right? Because you're going to have some helium left over. That's was not able to be fused because it wasn't hot enough. Now it's heated enough, so you get a new flash of that helium shell. And you kind of see where this picture is headed. So, and then further out, of course, there's another shell beyond that helium where fresh hydrogen can actually heat and be fused again. So it's got this multi-layered structure, kind of like an onion. The carbon-oxygen core, a shell of fusing helium, a layer of helium not fusing, a shell of hydrogen fusing, and then finally the outer layers of the star. Now, I guess it's worth pausing here to put some more kind of crazy ideas on your plate, which is that if you actually look at the layered structure of this, and this will be a lot more evident when we get to the supermassive stars' layered structures. But you actually get, this is a really interesting layered structure that in some sense approximates the structure of something like a Jupiter with its, potentially layered structure, or like a Saturn, right? It has a very similar composition at this point to something like that. So, an interesting thought experiment is if this thing was to just cool all of a sudden, what would it look like? It's like, well, it might look a lot like something like a Jupiter or a Saturn at this point. It would have a nice layered structure that would make it maybe a bit different than a brown dwarf. All right. So as all that heat flows outward from the two fusion shells, the outer regions begin to expand again, and the star moves back into the red giant part of the HR diagram. So the last time we saw this before, it was actually helium fusion that came to the rescue. But at this point, the fusion of helium requires such a ridiculously high temperature that these lower mass stars just can't do it. They can't compress their cores anymore. So a star with a mass similar to our own sun, the formation of carbon and oxygen is the end of the process here. And the thought is that a star like our own, assuming it doesn't lose any material, is going to continue to undergo that gravitational compression. And it's just going to get denser and denser and denser. There's no repulsive force to stop it. And so we'll talk about the fate of that, but the generally assumed fate is this strange object called a white dwarf at this point, right? And we'll unpack some different ideas about the white dwarf here. We have time for that in just a moment. But for bigger stars, we have a different story. So when they swell up to become these red giants, they have a really big radii which means that the gravitation at the edges is less, which means they have a pretty low escape velocity for the atoms in the outer surface, which means that the surfaces can essentially escape all of that material. You know, if we look at the surface of our sun, a lot of that material is held back by gravity. There's also a lot of electromagnetic cohesion, which people are still trying to understand how that contributes. But for whatever reason, the surface loses integrity, and you get these layers that start to flash off from the surface. You know, it's also lost a lot of mass by this point. So a star like our own sun, by the time it reaches the helium flash point, it's going to have lost something like a quarter of its mass already. It can still lose more mass when it goes into the red giant branch for the second time. So these aging stars are surrounded by at least one, probably multiple shells of expanding gas. And that contains, you know, that can contain 10, 20% of the whole star's mass. So the core begins to shrink, like I say. Heat, more and more heat, no fusion to push back. The whole star kind of follows along and shrinks till it's very hot. Surface temperature is getting really, really high, 100,000 Kelvin. Remember, the surface of our own sun is something like 5,000 or 6,000 Kelvin, so very, very hot. The solar winds, ultraviolet radiation heat the shell, ionize them, and set all of those outer layers kind of ablaze in what we call this planetary nebula, which is what you see here. These are examples of this final death stage of these low-mass stars. Now, it's interesting, we call these planetary nebulae, but they have nothing to do with planets, unfortunately. This is another one of those like ridiculous nomenclature experiences that we must suffer in astronomy continually. Of course, people originally saw these things in the sky and thought that they were perhaps planetary disks, but they're not. And so we still call them planetary nebulae, but they're really just the outer layers. That's all this dust and debris that's being shed from the star, getting ionized, lit up like one of these fluorescent lamps with all of the radiation coming off of the sun. And there's tens of thousands of these things in our own galaxy. Most of them you can't see because their light's getting eaten up by the interstellar dust. So to recap this process, it's essentially something of a recycling process, all of this, because everything that's flying off of these stars is going to go into the building blocks of new protostars in the future, which is a really interesting kind of cyclic nature to everything that exists in our world today. It's all a product of multiple iterations through this process of stars living and dying. What else do I want to say about that? Oh, it's a very similar process, yeah. So he mentions that the planetary nebulae look a bit like the aurora, the northern lights. And it's the exact same thing, actually. The northern lights are caused by ionized atoms, essentially, right? Also due to the solar wind. So it's the exact same process. In that case, it's concentrated at the north because we have this nice magnetic field that's shielding us from those same solar wind particles hitting us face on down here at lower latitudes. But at the north, there's something of an unprotected region, I think is the best way to think about it, right? It's a torus, right? So there's a little donut hole at the top where a lot of this radiation can still make its way in. And it's interacting with all those high energy particles are interacting with our atmosphere. Much like as the star is dying, its high energy radiation, its solar wind is interacting with the dust and debris and different condensations that are left over as it shed its layers. So it's a very similar process, yeah. Exact same process, really. But it's a planet instead of a star. All right, so now we have to think about, okay, we've figured out, we have at least have a reasonable hypothesis for where something like carbon comes from, right? Things as big as carbon, helium, hydrogen. And to be fair, most of the elements that we see in our daily lives consist of those, right? So plastics are more or less hydrocarbon chains, right? So it's hydrogen and carbon, right? Most of the atmospheres of the giant planets, which seem to be most of the planets that we see, are hydrogen and helium for the most part. So we've got all of our basic building blocks for things. But we do see around us quite a few other atoms, right? We see metals, things that are much bigger atoms. They must have been fused in something very different from our own sun, at least according to this theoretical model that we've built for ourselves. So where do we get things like gold and silver and things like this? This is a very different process, actually. So when these massive stars become red giants, they're so bright and big we call them supergiants. This is like Betelgeuse that we were talking about earlier. They're also really, really effective at losing their material, right? They have really dramatic winds and huge outbursts, as they're shown. We're actually seeing one here. This is a star that's something like 100 times the mass of our own sun. It's in the constellation Eta Carina, which is one of the biggest stars that we've ever seen before. And you can see it's shedding all of these layers quite violently. So the layering structure is a little bit different here. So the crucial way that these massive stars are different than the story that we've talked about up to this point is they can start different kinds of fusion in their centers than we would get in a star like our own. So when your outer layers of a star that's in the stars, let's say something like 8 times as big as ours, they have enough weight to actually compress the carbon, and actually oxygen can be made, which is just a little bit bigger than carbon in a normal star like ours. We didn't talk about oxygen, but it's not too much different. But they can actually compress that carbon-oxygen core until it becomes hot enough to ignite the fusion of the carbon nuclei themselves. So carbon fuses into more oxygen. At higher temperatures, the oxygen, and then it can fuse into neon, magnesium, finally silicon, which is a huge building block for our own planet, right? If you think about most of the rocks under our feet are silicate. Our whole mantle is essentially silicate. And so iron turns out to be the absolute bedrock of what you can fuse, the biggest element. I can't remember off the top of my head, but iron is somewhere on the order of 50-ish times the mass of hydrogen. So it's quite a big atom, but it's not as big as some of the things that we see, right? So, plutonium, for instance, or some of these really huge atoms are hundreds of times the mass of hydrogen. And so even though we can make some pretty big atoms in the cores of these stars, the biggest stars that we see don't seem to be big enough to make anything bigger in their cores during this red giant phase than iron, which is really an interesting predicament. So where in the world do we get all of those other elements from? Now, we're going to start talking about some violent ends to these stars, in particular the supernova. And the basic idea, which we'll get to in a little bit more depth here, is that the only way you get things bigger than that is through these actual explosions, where you have enormous shock waves as these stars rip themselves apart. And that in those actual explosions, you get the temperatures and the collisions necessary to stick 2 irons together or something like that in order to make these really, really heavy atoms. So that's an interesting hypothesis, There's other possibilities too, right? Like, how about the center of the galaxy itself, right? There's enormous pressures possible there, huge collisions. There might be other places where we could expect those fusions. And then, of course, what about Cebulski's star, right? What about the idea that there might be some sort of other kind of fusion processes happening in stars that aren't even dying yet? That'll certainly change this story quite a bit. But as far as the textbook's concerned, all of these massive elements are being made during supernova. So, what do I want to say about this? Going back to this cluster idea a little bit, in the sun, in most of its neighboring stars, the combined element abundance, so the relative amount of elements bigger than hydrogen and helium, is really small. It's something on the order of 1, maybe as much as 4% of the star's mass. in the most open clusters are going to be very similar to this. They're all kind of similar to our sun. Globular clusters are a little bit different. So the heavy element abundance of stars in typical globular clusters is only something like 100th, maybe a 10th of that in the sun, which is really quite interesting because they're supposed to be the really old ones, and yet they have far less of these heavy elements. The idea is that the first generation of stars in these clusters contained only hydrogen and helium, but in order for those stars to make their power, they create these heavier elements in their interior. And then in the last stage, they eject all of this matter, which goes off and becomes reservoirs for the new stars like our own. So we see these heavier elements because we're incorporating them in order to make our own star systems later, which seems reasonable to me. Okay, so the first generation of stars that formed in our galaxy wouldn't have been accompanied by planets like Earth, as this model goes, right? Because Earth has tons of silicon, iron, and heavy elements. You would have seen only things that looked like Jupiter's, maybe Saturn's, things that basically looked like very similar to, in composition to stars themselves, run-of-the-mill stars like our own. So when we're looking for these first-generation stars, we expect that they would be quite massive often, live really fast and die quickly, and that's why we don't see many of them. They probably died a long time ago as far as our own galaxy's evolution is concerned. So the best place to look for them is in other galaxies, and we'll see that when we start exploring beyond our own galaxy next week, I guess. All right. Questions at this point? I know this is all quite technical, but it's important to have a grip, at least an overview of how this goes down, particularly because starting next week, we're going to start exploring the really esoteric arms of astrophysics, right? We're going to work towards this idea of black holes, which is an absolute darling of both the science community, but also of the science fiction world. And we're going to have to in order to do that, we're going to have to take a pause and consider Einstein's theory of general relativity and this idea of what space and time really are and what those things mean. And I think you'll find that I'm quite skeptical of a lot of these extraordinary interpretations of these theories. But I want you to understand why I feel that way. And so we have to understand the normal path that stars go through, because up to this point, we reach this point where these stars are losing mass, they're getting rid of a lot of material, and the story goes that they are collapsing under their own weight gravitationally at this point, which results in the production of, well, a number of really interesting things. The most, the easiest one to swallow is this idea of a white dwarf, which we'll talk about next. The more difficult to swallow one is the idea that it collapses so much that light can no longer even escape from it, and we get this thing called a black hole. And so let's see if we can make sense of that. Now, there's serious problems with those ideas too. I mean, this idea that a system can do work on itself is in some sense theoretically controversial to begin with, right? So, you may have learned, I don't know, if you've taken some basic chemistry in high school or something, you may have learned one of the thermodynamic laws of the universe is that a system can't do work on itself. So, for instance, you can't generate energy by, if you're in a vacuum by yourself, you can't generate energy. Let's leave it at that, right? Thermodynamic systems are closed. And so there's no way for you to actually create energy. You can't, you could say, well, I could rub my hands together and stay warm. And it's like, well, you don't have any food. And so your mitochondria are eventually going to stop making ATP. And you're going to basically die and get cold eventually. So you won't be able to keep rubbing your hands together. So you might be able to transmit the energy from one form to another, but you can't really create energy. Now, the proposal that a gravitational system alone, that essentially the atoms can do work on themselves by pulling themselves together enough to the point that they actually are producing anything, is in some sense a little bit hindered as far as I can tell, right? It doesn't seem to be thermodynamically possible that something can do work on itself. And so what's actually going on? Let's start off with the traditional story of the white dwarf. So we're looking at these low-mass stars, right? After they've shed all their layers, that core is thought to continue to contract under its own weight. And you have this new appearance. So these white dwarfs, if you look on the main sequence, what we're trying to do here is explain the appearance of these really dim but hot bodies in the sky. So these stars that appear to be really hot. They're blue, white blue, like a flame, right? The hottest part of the flame, but they're really dim. And so in some sense, astronomers didn't really know where to put these. They saw them on the HR diagram. They knew there's this cluster of bodies. They explained the other ones that are off the main sequence as this story we've told of these expanding giant stars, right? But how do we explain that pocket of stars down at the bottom left? These very hot but small stars. And so the idea is that, well, those are the leftovers after the stars have died. There's another possibility too, which is that we gauge the luminosity, like we talked about, if you can remember all the way back to the beginning of the course when we were talking about this idea of luminosity. It's like, well, luminosity, especially in the mass-luminosity relationship that we use to stick these things on the HR diagram ultimately, luminosity, the mass-luminosity relationship depends on the ability of a material to absorb light, because if you can absorb light, then you can give off light. And so if we're trying to judge exactly how big something is by how luminous it is, we have to assume that its material structure remains unchanged. Let me put this to you another way. Carbon, right? Graphene, soot, let's say, is used in these black body experiments to give us the temperature. So if we have a soot-covered chamber, we heat it up to a certain amount, it gives off a color spectrum of light that tells us the temperature. Well, what happens if you, instead of having graphene, or essentially this hexagonal planar arrangement of atoms, what happens if you arrange the atoms a little bit different and you arrange them in a more of a tetrahedral structure? You take the same carbon atoms, don't do anything to them, you just make a crystal that's a little bit different lattice structure. Well, you could have something like diamond in that case. Now here's the thing. Diamond, you could heat it up all day long and you're not going to get a black body spectrum from it. So you might think that the diamond, despite the fact that it's really, really hot, you might think that it's, say if I heat up let's say I have a ball of carbon here, a ball of carbon here. The only difference is this one's diamond and this one is graphene. And I go to the end of a long hallway and I heat these things up to the same temperature. The one that's soot is going to appear quite bright to you, right? It's glowing like a coal. The diamond's not going to glow at all because it has very little emissivity. It has very little absorptivity. It doesn't interact with light the same way, right? And so you're going to think that this guy is actually really, really small, even though it's the same size as this one and they're the same distance from you. So this is why I spent so much time at the beginning of the course telling you how important and revolutionary the study of the material lattice structure of stars is going to be in the next century. I think it's going to absolutely revolutionize all of the stories that I'm telling you today. All of these stories are going to have to change because as long as we treat the star as a burning ball of gas, we don't have to deal with lattice structure. This concept that I'm bringing into you, it doesn't matter at all because gases don't have lattices. They don't have a crystal structure to them at all. Now, liquids do, actually, it turns out. You might think of a liquid as just these random atoms that are flowing around, but actually, you can transiently observe that there are lattices that appear in a layered-like structure in water. You can see them. The atoms might be switching out of the lattice at any given moment, so there's still flow, but they're fitting into the position in that lattice. And water actually makes a hexagonal lattice much like soot as well, which is quite interesting. And we'll play with that more when we get back to the CMB later. So I guess what I'm trying to say to you is that we have this population of stars that is very hot, right? But it appears to be really dim too at the same time. And so we say, okay, well, those must be super massive stars because they need all of this mass to make that temperature be really high. And they must be really, really small because their luminosity, their surface area is small. And I'm saying, Well, there might be another possibility at play here too, which is that, yeah, they might be really hot. Their lower layers, their core might be really hot. They might be quite massive, actually, true. But they might not be that little, right? If their lattice structure, if in fact stars have condensed matter in their outer layers, if they do have a liquid or transient lattice, if they're not just simple gases like we modeled them, then it might be a pretty fat star, actually, that just has some sort of change in its lattice arrangement of its outer layers of that hydrogen that allows it to be a bit more translucent than something like the normal sun that we think of right now, which might have a very different lattice structure. So this, I think, is all on the move right now. And I just want to make that clear to you guys that I think this story is going to change quite a bit in the future. But all that being the case, let's talk about the standard narrative for these white dwarfs. So the idea right now is that this isn't the case, that these bodies continue to contract. They contract and contract and contract. They're super hot, and they're very low luminosity because they're so small. That's why the luminosity is so low. That's why they're on this strange part of the HR diagram. And they're so dense at this point that the concept of an atom starts to fall apart a little bit. They're actually considered to be something like a degenerate gas at this point. What's that mean? Well, plasmas actually in general are also degenerate gases. It just really means the electron, the shell of the atom doesn't belong to one atom. They kind of share their shells. They're all melted together in some sense. Now, what's kind of funny is that it seems like having a degenerate electron gas, it's like these white dwarfs are primarily composed of this degenerate electron gas. But what's really interesting is that a metal also is technically a degenerate electron gas. Now that's really weird because you might think a metal is like solid. Why in the world would we call it a degenerate electron gas? Because it behaves exactly the same. Metals also behave as if their shells of their atoms, the electron shells, are all fused together and interacting as one. This is why conduction is possible in metals for the most part. So it seems like a really exotic kind of material, but it's also, in some sense, technically identical to a metal. At any rate, they're thought to be extremely hot, extremely dense, and extremely small. So the idea is that at this point, if nothing happens, and this is thought to be what happens to our sun after it loses its outer layers, right? A normal run-of-the-mill dwarf star like our own. At this point, nothing happens. It's not accreting any more material, right? So it's not necessarily getting hotter beyond some points. And then the idea is that over maybe billions, perhaps trillions of years, this thing will just cool off. And it'll just have kind of a slow, quiet, textbook says death. I might say metamorphosis, right? Because the central region of these white dwarfs is still a mixture of carbon and oxygen at the end of the day, especially as it cools off. There's a thin envelope of helium. And so, you might imagine, what would this thing look like after 1 trillion years after it cooled off? It's like, well, a big ball of like carbonaceous rock, maybe something, it would look something like an asteroid or a moon or something like that, which is quite interesting because, well, we're going to play with the age of the universe here in a couple of weeks, which seems to be really an open topic of debate right now. Well, most people would say that the universe hasn't, formerly, let's say, throughout the 20th century, people would say the universe hasn't been around long enough for any of these objects to cool off and become anything like a moon or an asteroid, right? But what if we decide that the universe is much older than 14 billion years? What if we decide it's 30 billion years? What if we decide that it's 1,000 billion years, trillion years old? Well, now we have time for a lot of these things to have actually cooled off. Now we might have to start considering the provenance of some of these deader-looking bodies that are out there and wondering if they aren't perhaps the leftover cores of some of these old, dried-up stars, which is a tantalizing possibility. I think that also is something to watch out for in the next few years as this Big Bang narrative shifts a little bit. And I think it's hard for us the reason that I'm bringing all these things up to you is because it's hard for us to understand who cares. I think let's do like a show of hands. How many people here have ever really thought about the beginning of the universe before? Okay, most of you, half of you, let's say. But I think, and of course you guys signed up for an astronomy course, so that's self-selecting for people who probably care about these things a little bit in the first place. But I would say most people don't really think about this stuff. It's hard to. I'm a real party killer. I don't think that most people care about these matters too much. Now, the reason that something like the birth of the universe actually matters, as far as I can tell, as far as science is concerned, anyways, you might have metaphysical reasons for caring about the beginning of the universe. But as far as understanding what these material bodies are doing up there, the reason it matters is because it puts a time limit on how fast a lot of these astronomical bodies can form, right? And so it really constrains our theories about where some of these objects come from. And so, as those timelines change, so are the theories of how the planets formed, so are the theories of how the moons form, things like that, which is, I think, quite interesting. So now, the idea is that these white dwarfs, let's say, this radius is gauged based on luminosity, right? The idea is that as something has a really high mass and a low radius, at some point, it reaches a limit. There's only so much mass that you can have before you've squeezed the thing down. If you're just applying basic Newtonian gravitational principles, you're crushing these atoms down, and there's a limit to it, which is called the Chandrasekhar limit. What's quite interesting here is that this entire model, by the way, once you reach this Chandrasekhar limit, what happens? Well, we end up in this bizarre esoteric place where we've, in all technicalities, reached the edge of the limit of the model. However, we know that there are bodies that are much more massive than this. And so what happens to them? Well, that's where we get into the realm of black holes, which we're not going to do today. But, one interesting way to start thinking about what a black hole is it's where something has reached beyond the limits of our model, right? We've gone off of the map, let's say. So that's an interesting context to think about this in. Now, if what I say turns out to be true and that the stars are not reasonably considered to be burning balls of gas and that they actually have some material structure, however you want to describe that, as a liquid plasma or something, and that we have to actually start considering the emissivity in the luminosity calculation, if we have to start considering that lattice structure, then this entire model goes out the door. And we have to reconsider why exactly these things are less luminous. And it might not have anything to do with the fact that they're shrinking. It might really just have to do with a lattice transformation on their surfaces. And so if that goes, then all of the story that follows goes as well. And when we have a lot of work to do to catch up. And I have a sneaking suspicion this is going to be the case in the next 50 years. So all right, so if the birth of the main sequence star is defined by the onset of neutral hydrogen fusion, then the end of all the fusion must be considered the time of the star's death by this analogy to living systems. And you can see how the star moves down into that lower left. This is the theory, right? So as the star is down its wiggle up there in its giant phase, then it's slowly collapsing down and moving into this dim but hot phase where it lives as a white dwarf. This is the standard story that I've painted for you up to this point, just to review it. I should have put this slide earlier, but it's quite interesting. These white dwarfs, like I said, eventually they're going to lose all of their heat if you just leave them there for billions of years, right? They call this hypothetical entity a black dwarf, actually, once the white dwarf has lost all of its heat and it's no longer radiating. These things are composed mostly of carbon, oxygen, neon, products of all of the other reactions that it was capable of, maybe some of the heavier stuff. And that's a really, really similar composition to a planet, which is really quite interesting. So I hope you guys can see how much these timelines actually really matter and why we're going to spend so much time picking apart this Big Bang theory later. Because, the Big Bang Theory is actually quite new as far as science is concerned. Most scientists before the 20th century had a more, let's say, eternal vision for the cosmos. They kind of had aligned themselves very antithetically to the religious narratives that insisted that the whole universe was on the order of thousands of years old, and they knew that wasn't the case. So they kind of threw the baby out with the bathwater, and they had this eternal conception of the universe for the most part. This idea of the universe actually having a beginning wasn't solid, let's say, consensus science until maybe the 1960s or 70s, and they were still arguing about it up into the 80s and 90s, quite seriously. And it was only sort of consensus accepted in the last 20 years, and now it's on the ropes again. So I hope you can see why this matters so much, right? Because if the universe doesn't actually have a birthday, which is a radical statement in this day and age, but if it doesn't have a birthday, then this is a very reasonable way to make planets as well. That's what's exciting and interesting about it. To support that idea as well, I brought this up before, but I wanted to show you some pictures. There's this study that was done over the course of 30 years where this woman, an astronomer in Spain, I believe it was, she went back through all of these naval archives because the Navy, is of course the Defense Department's intelligence agency, more or less. And they had been photographing the night sky. I think they were trying to find, Russian satellites and stuff back during the Cold War years. So they had all of these really nice time-lapse photos of different regions of the sky. And she was examining these. And I don't even know how she got started doing this. I don't think I even asked her. She did a podcast with us, and I'd highly recommend you check it out. But she found something kind of extraordinary, which is that a lot of stars, or what appear, let's say luminous objects is what she calls them, because she doesn't want to piss anybody off. A lot of these luminous objects, which you would probably call a star if you went out and looked at the sky, they disappeared, actually. Now, what's really interesting is that we're going to start talking about supernova and different types of explosive ends of stars. And this is when you talk about most people, that you talk about the death of a star, most people think of supernovas. But we actually haven't seen a supernova in our own galaxy since Galileo's time, which is really shocking, actually. So, many astronomers will tell you, well, they're still happening, we just can't see them, they're stuck behind dust or something like that. Maybe. But is it possible that stars are dying in a very different way? I mean, this Vasco study is really compelling piece of literature. You can read this too, and she's doing a follow-up on it now as well. It's called Vasco, V-A-S-C-O, Vanishing and Appearing Sources. There was also stars that appeared too, which in some sense I think gives credence to this idea I've been playing with, that brown dwarfs could potentially turn into an actual luminous fusing star phase for some portion of their lives and then go back to being brown dwarfs, right? I think that we're not going to be able to ignore the dynamics of these systems, that maybe it's not as simple as you're a brown dwarf forever or you're a sun forever, right? Maybe you can spend part of your life, maybe you spend multiple phases of your life in one or two of those different stages. And this lady is so careful. I tried very hard to put these ideas in front of her, and she just didn't. She's already under so much heat for even publishing this study. And she did a really, really good job. The paper is very careful. She says, well, she tries to rule out everything from artifacts on the photographic plates to satellites to she even goes into the black hole theory. Maybe some of them turned into black holes. She's trying to be really generous with what could have happened to all of these. She won't even call them stars. She calls them luminous objects, right? So she's just such a careful lady. She didn't want to have anything to do with the theoretical explanation. She's like, look, I'm just publishing what I see. Somebody else can explain it. I'm already in enough heat for publishing this, so, leave me alone with your ideas about what it means. And it's kind of unfortunate. It's, this might sound super drama rich for most of you, but something happened something very pernicious happened back in the 1950s when science became a career for the first time. It's hard for us to imagine, but for most of the history since Galileo's time, science was done by people just for the hell of it, for lack of a better phrase, right? People were just really interested in how things work. Most of the people who were doing all of this work, when we think about the real forefathers of this, all the way from Newton and just going back to like the real titans of science, Huygens, like these people were wealthy, right? They were like landed gentry. Maybe some of them were doctors or lawyers. They had jobs, maybe they were politicians, but most of the people doing science weren't making money off of it, right? Something happened after World War II where the states, let's say the United States, or all the states for that matter, realized that the scientists were the ones who were giving them the technology they needed to strengthen and embolden their states, right? They were building the military technology, the airplanes and the weapons and the bombs and the spaceships and all of these things. And they were like, you know what, we should probably keep these people in our stable after World War II. And so they started actually supplying grants for the first time, government grants, huge chunks of money, relatively speaking, to, when you go from having zero money in science to having government grants to do it, well, it turns into a very different ballgame all of a sudden. And you see a lot of fear, actually, I talk to a lot of scientists all the time. It's my job, basically. And everyone's very, very afraid to go out on a limb, particularly in the theoretical domain, right? There's a narrative, a story, let's say, for how stars formed and died that you inherited from the generation before you. And you can get grants to work on that, right? You might be able to study some little piece of that story. But to go and actually attack the legs that the entire narrative is standing on is, well, it's essentially impossible to be funded for starters. But worse than that, people are very afraid that if they have ideas that contradict this whole giant that's kind of lumbering around, that everyone will turn on them, which they will, because everybody likes that giant because it's providing them a good paycheck at the end of the day. And so it's not to say that like the individual scientists themselves are corrupt, but there's a lot of self-censorship. There's a lot of people who will, before the camera is turned on, like I do this podcast, right? This is like my main job. I'll have incredible conversations with people before the camera comes on. I put the camera on and people just lock up like the 10 man, right? It's just like, and I've honestly I've moved away from interviewing a lot of academics because of this reason, because they're just so boring on camera. Like they won't play with ideas in interesting ways. They won't, even if you're like, hey, it's okay, like we're just playing with this idea. We don't even have to say it's true. It's just like, well, what if this was the case, then what would this be, right? And this is the old Descartesian idea or Cartesian idea of the hypothesis, right? Which was an instrumental part of science originally. It's like, what is a hypothesis? It's just a playful idea that you're not saying it's true. You're just saying, if this were true, then what would happen, right? And then ideally, once you think of, or like, oh, wow, that would explain, the appearance of a planet, for instance, right? If the stars actually cooled off and they had enough time to cool off, well, then they would look just like a planet and we would overcome a lot of the problems we talked about last week. Like, how do you make something that's the most dense body in the solar system outside of the sun, which is what we're standing on right now? It's 5 times denser than the sun. Well, maybe if the universe was old enough, you would have plenty of pressure in the center of a star to make something this dense, right? So that's a reasonable hypothesis in that case. But that sort of hypothesis is completely off the table for most people because the megalith of the Big Bang cosmology precludes it from the discussion. So it's not even something people want to talk about while the camera's on, right? People are very afraid of not getting funding. It's something of a tragedy. And of course, it's led to incredible technological blessings for our civilizations. So like, I don't want to kick this machine without being really cautious about it because, it's not entirely clear how we go about funding technological development as a people. Like, how does our government do that without concretizing in these theoretical pursuits as well? Like, how do we produce a space where people can play with new ideas in a non-threatening, like, honestly, in a safe space where they're not worried about getting their next paycheck, and still produce incredible technology at the same time, which requires a very rigid funding structure and so forth. It's not a problem that has an obvious solution to it, I guess. So, this paradigm that I'm kind of playing with right now, this stellar metamorphosis idea, that perhaps given a long enough time that the cores of these stars, these cooled off cores, could evolve to look like planets. This idea was actually proposed first by Aristotle long time ago. He thought that the planets were basically cooled off stars. Later on, there was a Soviet scientist in the 1960s named Oparin, who was actually quite famous for his work. He was a chemist, actually a biochemist, and he was, the way that, this is actually a little aside here, Russian science is quite fascinating. A lot of it's completely insane, but the Russians weren't part of the Western dialogue during the 1960s, so they had very different theoretical underpinnings to their science than we did here in the West. They weren't, under the pressure of the same academic structures as we were. And Oparin wrote this book called, I believe it's called The Origins of Life in translation. And in it, he proposes just that he tells this story for the Earth where it used to be actually a sun that was glowing and it cooled off, and all of these chemical reactions he lays out lead to the production of all of the complex molecules that are on the Earth. It's a really, really tantalizing idea. Now, of course, that's a perfectly reasonable idea if you don't have the preconception that the universe is very young, only 14 billion years old, right? And remember, our sun is under this same model is thought to only be 4.5 billion years old. And it's a second or third generation star, which I'm not even sure how you possibly pull that off in 14 billion years. But that's the narrative we're stuck with. Well, the Russians didn't have that narrative, right? So their conception was that actually, well, if you look at the layered structure of one of these massive stars right before it goes supernova, right? Well, look at this thing. Iron at the center. It's got silicates, sulfurs, oxygens, carbons mixed with oxygen, and a bit of helium and hydrogen on the outside. It's basically the Earth, right? If you mix up these chemicals, if you mix some of these elements together, you get all of the molecules. You get the water. You get the silicates in the crust and the mantle, right? It's basically already structured like a rocky planet to begin with, right? So, there's something to that. And even if we stick with this very, let's say, well-defended and very popular idea that a star like this is about to explode, which is where I'm headed with this next. Well, what happens to the chunks of all that stuff, right? Do you get little chunks of little planetoid chunks that are left over in the aftermath? Is it possible that as opposed to this accretion narrative that we have, that all of this dust in the disk of the planet accretes somehow under its own gravitational pressure to make something like the Earth under our feet 5 times as dense as the sun? Is it possible that it had some starting blocks at least to begin with? Did it maybe have a core left over from some exploded dead star in the first place? I mean, this is kind of the diet version of, it's kind of the weak version of the stellar metamorphosis hypothesis from Oparin, right? It's like, okay, yeah, you can have the star explosions that make the building blocks for the planets, but maybe those building blocks are pretty big, actually, to begin with, right? And so, this diagram in particular had a really, this is when I first came across this, my friend Jeffrey showed it to me, and it really took me aback. The more and more I looked at it, and the more I looked at the structure of our own planet, the more I was just really blown away by it, and as opposed to how similar the two are in their own structure. So we have this massive star at the end of its life. Now, at the end of its life, when all these reactions stop, the massive star is also like a white dwarf, becomes supported by this degenerate matter. So the idea is that it's collapsing, it's being squished so hard, the atoms stop really having the form that they're used to having. Still grows. At some point, the iron core, the story goes, that it reaches a mass so large that even these degenerate electrons, the pressure that these degenerate electrons, these shared shells, can no longer support it. And the core itself begins to shrink even more. Now, these densities that are proposed are something like 4 times 10 to the 11th grams per centimeter, which is something like 1 billion times the density of water. Now, no one's ever seen something so no one's ever created something the density 400 billion times that of water, right? This is entirely theoretical. It actually sort of strains the imagination. And remember, we've kind of left the theoretical map as far as what we're we're able to even imagine at this point. But story goes that the core continues to shrink more or less indefinitely. And at some point, we're left with, the atoms have no shells whatsoever. It's just nuclei. And in fact, these neutrons are crushed together, so they're essentially one homogeneous substance as well. Oh my gosh, I just realized I've gone over. I'm sorry, I was rambling. All right, we'll pick up here next time. See you guys Tuesday. I'm sorry about that.